right, so we're going to talk about the transformations of functions. So there are several common graphs here. Here we can see that this is a constant function. This is an identity function where x and y have the same values, so x is equal to y. So when x is negative, or x is 1, y is 1, x is 2, y is 2, they match up there. So that's an identity. This is an absolute value function. This is our standard quadratic, which we call a parabola. That's just an x squared function. This is a square root function, and this is a cubic function. Now, with these standard functions, we can actually manipulate these functions in several ways. So we can do vertical shifting, where when the addition is on the outside, or subtraction, it's going to raise the graph or lower the graph up and down. That's a vertical up and down. The horizontal, think about it stuck inside the parentheses, so it can only go back and forth. So when it's inside, it's going to shift the graph left and right. And this one will go opposite of what you think. So this one goes exactly what you think. When you add, you go up. When you subtract, you go down. But when it's a positive inside, you're actually going to go to the left, and when it's a negative, you'll go to the right. So it's kind of opposite of what you think you see. A reflection about the x-axis, it's going to be a negative on the outside, and so it's going to reflect this way over the x-axis. If it's on the inside, it's going to reflect for a y-axis. Now with vertical stretching and shrinking, if you have the value multiplied on the outside and it is greater than 1, then it'll stretch it. If it is between 0 and 1, then it will shrink the graph. And notice the vertical again is on the outside, but the horizontal is on the inside. And when it is greater than 1, it will shrink it. When it is between 0 and 1, it will stretch it. So let's actually look at some graphs. So for the vertical shifting, here we can see when it's being added, it goes up, and if it's being subtracted, it's moving down. So we can see an example of this. If we have a regular graph of f of x equals x squared, and we change it to x squared plus 2, and x squared minus 3. So the plus 2 will take our regular graph that's right here, and it's going to move every coordinate up by 2. The minus 3 will take every coordinate and move it down by 3. So we can actually do the t-charts for that so that you can see the values of what's actually going on. So we're going to look at our f of x equals x squared, our x squared plus 2, and our x squared minus 3. So this will be example 1. So for f of x equals x squared, if we make a t-chart for this, we're going to use the same values. So I'm going to pick negative 2, 0, and 2. I don't like my values too close together because it's hard to see what's going on with the graph. So if I plug that in, I get negative 2 squared. Well, negative 2 times negative 2 will get me positive 4. 0 squared is going to get me 0, and 2 squared is going to get me 4. Now, if I look at my g of x, which was equal to x squared plus 2, if I make another t-chart, I end up with, I'm going to use the same values so we can see what's going on. So I have negative 2 squared plus 2. Well, negative 2 squared, again, is going to get me 4, plus 2 will make it 6. And then 0 squared plus 2, 0, plus 2 will get me 2. And then if I plug in my 2, 2 squared plus 2 will get me 4 plus 2, which equals 6. So notice the same values, but it's added 2. Here it's gone from 0, and it's now at 2. Here it's gone from 4, and now it's at 6. So each of these values have added 2. The same thing will happen if we take the h of x equal to x squared minus 3. We're going to use the same values so that we can compare. So we have negative 2 squared minus 3. Negative 2 squared is still 4. Minus 3 will get us 1. And then 0 squared minus 3 will get us 0 minus 3, which is negative 3. And 2 squared minus 3 will get us 4 minus 3, which is 1. So if we go back to our original graph, 4 minus 3, oh, that's 1. 0 minus 3 is negative 3. And 4 minus 3 is 1. So you can see that from the original function, this is moving the graph up 2, and this one's moving everything down 3. If we took these points that we have here and we plotted them, these were the graphs that we would have. And we can see exactly what's going on. So you can actually just make some t-charts to figure it out. Now the stretching and shrinking, sometimes it goes opposite of what you think, but let's look at what's going on here. So when c is greater than 1, so this is the original graph, the one on the inside is the original graph. When it gets multiplied by something, the y values grow. So think about if I have, like, my function is like x, this is like an x cubed kind of thing, but it's just a graph that we're just kind of looking at. If we were looking at, let's just say that our f of x is just x, just so that it's easy to look at. It's not an x function, but if we just think about it that way. If I multiply it by 2, then everything that, whatever it is, it gets multiplied by 2, it gets doubled. So it gets pulled up. It would be like 2x. And it would get pulled down this way as well. So I don't know what the function of this, I'm just saying, because they're just using it. Notice on these vertical stretching and shrinkings that the x values stay the same, but it's the y values that change. So it goes up. So on these, we're looking at our c has to be greater than 1, so that's why I'm picking a 2. It would double it, it would pull it up. Now, if I look at shrinking, where it has to be like a half, so it has to be between 0 and 1. So again, if this is my function and I multiply that function by 1/2, it cuts all of my y values in half. So this is the original function right here, and then when I multiply it, it's going to shrink. Notice again, the x values stay the same, but the graph gets closer to the x-axis. So here is an example. So here we have f of x equals x cubed. So this is just the regular graph of it. Now if I multiply it by 1/2, see what happens to the graph? It gets kind of squished down. It's becoming shorter. It's spread out. You can see how it comes quickly up, and now it does not. So the points are changing. Here at 2, we're at 8, but here at 2, we're at 4. So my y value got cut in half, because 8 divided by 2 would be 4. Same thing happens over here with the negative values. So the next ones we're going to look at is horizontal shifting. So you can see here, if this is my function, when I add c, it scooches over to the left. When I subtract, it's going to go to the right. And we can see this happening with these graphs. So x squared, f of x equals x squared if we start with the regular parabola in the middle. And then I add 2. The adding 2 will move it this way. If I subtract 3, it will go this way. So we can do the same thing with the t-charts. So let's go to example 2. So again, we're going to use our same functions. So we have f of x equals x squared. We have, this time, they have h of x is equal to x plus 2 squared, and g of x is equal to x minus 3 squared. So it's similar to what we had earlier, but a little bit different. So we're still going to create a t-chart. And we're going to use the same values of -2, 0, and 2. So this is going to be the same as the one up there. We're still squaring everything. It's still an x squared, so we're going to end up with 4, 0, and 4. Over here on the next graph, though, we're going to use -2, 0, and 2. But when we plug it in, we get -2 plus 2 squared. Well, -2 plus 2, well, that's going to get me 0 squared, which is 0. And 0 plus 2 squared will get me 2 squared, which is 4. And 2 plus 2 squared equals 4 squared, which will get me 16. Now, when we go to the g of x, we are looking at doing our t-chart again. So x and y, -2, 0, and 2. So here we have -2 minus 3 squared, which will get us -5 squared, which will be 25. And then 0 minus 3 squared equals -3 squared, which will get us 6. And then 2 would be 2 minus 3 squared. So 2 minus 3 would be -1 squared, which will be 1. So as we graph our equations, the first one will graph exactly the same. And then this one, if -2 is at our 0 point, if we come look here, at -2 is our 0 point, that's where we're at. So it's moved over. And then our other two are this side of the parabola. And we still need to figure out this side if we wanted to kind of graph it, or we can kind of mirror the image. On the other graph, when we subtracted 3 at -2, we're at positive 25. So we're on the high side. When we get to -2, we're on the high side of this graph. Our 0 is at 6 for our y. We don't even know what the x-intercept is. We'd have to do another number. We'd have to do 3, which is where the intercept is. So if I do 3, just so you can see this, I get 3 minus 3 squared. Well, that's 0 squared, so that would get me the 0. So you can see that the value ends up being right there. So it really does work out that way with the y. It's opposite of what you think it is. And the same thing would happen when we come down to this. We could do the same kind of values. Whether we have a square root, it's the same process. So if I am looking at the square root of x that looks this way, the square root of x plus 5, it's still inside the parenthesis type thing. It's underneath the radical. The values are going to push it to the left 5 values. So the same thing happens whether it's parentheses or if it's some kind of grouping like a radical. So now we're going to look at our horizontal and stretching and shrinking. So remember when I was talking about the vertical, remember the x values didn't change, but the y's did. Now if we look at this, for the horizontal stretching and shrinking, notice that the x values are the ones changing, but the y values do not change. So when it's shrinking, if this was the original function, it's getting shrunk in this way. And with the stretching, it's getting stretched out this way. But the y values will stay the same. This time, it's the x values that will change. So you can kind of see that with this function. They multiplied by 2 on the inside. So this is the original function. Now everything changes, and we see that the x-coordinates are actually shrunk by 2. It went from -4 to -2. It went from -2 to -1. It went from 2 to 1. So they are the ones that are changing in the graph. again, I'm not sure what the function of this is, but they're just showing you that they're multiplying by 2. This is the reflection about the x-axis, so this is where it's going to mirror. We can think about, like, if it's f of x equals x squared, if we have a negative out front, that the g of x equal to negative x squared. And reflection about the y-axis would take it and it's reflecting the opposite way. So this is like a cubed root of x and the negative of cube root of x. So let's go look at a couple more functions, and we will do some of the graphing of them. So we're going to do example 4, and we are given f of x equals x squared as the original function, and we want to change it to x plus 1 squared minus 3. So we're doing a couple of things that happen. What we want to do first is figure out what's happening with our graph. So what's happening here, it's on the inside, so that tells us it's going to move by 1, but because it's on the inside, it goes opposite of what we think. So it's going to go left 1, and that negative 3 will tell us it will go down 3. So if I take my original function, I'm going to put like 4 hash marks on, and let's see how that does for us. Here's our x and our y. So if I start with an original x squared graph, know that it always plots at those 3 points, the 0, 0, 1, 1, and negative 1, 1. So that's the original f of x. That's this one here. And now I want to move it to this one. So this tells me I have to go down 1, 2, 3, and over 1 for each point. And down 1, 2, 3, and over 1. And if I go down 1, 2, 3, and over 1, you can kind of see that. Or if you know that those 3 points plot like they do, once you find the vertex part there, you can just kind of graph it. And we're just sketching, so we're just trying to kind of sketch it out. So that would be this graph over here. All right, let's look at example 5. So for example 5, we are looking at f of x, again, is equal to x squared, and h of x is equal to x minus 2 squared plus 4. So with words, I want to say what's happening to the graph. So minus 2 tells me it's going to go to the right 2, because it's going to go opposite of what I'm thinking. And the positive 4 is exactly what I think. So it's going to go up and down, but this case it's going to go up 4. And so I can draw that out again. And I think let's go about 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, and we'll put like 2 down there. All right, so our regular graph would be those 3 points. And now we need to change it by what we've decided. So right 2 and up 4. 1, 2, 3, 4. And then I know that it's going to graph at those 3 points. All right. Next thing we're going to look at is a bigger problem. So let's do example. That last one was example 5. We're on example 6. So if we look at f of x equals x squared, and g of x equals negative 2 times x plus 3 squared minus 3. So we're going to combine a lot of things together for this one. So for this, we are looking at we're going to look at all the things we should start with. First of all, let's look at the horizontal. So the horizontal part is going to tell us that we are going to go left 3. And the vertical, or this part, let's do this part here. So this is going to tell us that we're going to multiply by 2. This one tells us we're going to flip it because we're going to reflect it. So we're going to call that flip or reflect. And then this tells us we're going to go down 3. So let's draw our graph. I'm going to make this one a little bit bigger because we have a little bit more to do here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All right, so again, original graph starting right here. And now let's see what we can do with this. So first of all, we have to move it over to the left 3. So 1, 2, 3. So it's going to land like right here. Then what we need to do is multiply it by 2. Well, when it's at this spot at the 0 for x, it's not going to change anything. That won't get multiplied, but these will. So this is actually going to go up to 2, and this one will go to 2 right there. So now we're at these 3 points. Now we have to reflect it. So we're going to flip it over, and we'll be up 2, so we're going to be down 2. So we're going to be down here and here. And then we've got to move it down 3. So we're going to go down 1, 2, 3. So we're going to land here. And then it'll be 2 more down, 2 more down. So our graph ends up being here. So we kind of did all of it together where we're moving it over, we're stretching it up, we're flipping it over, and then we're moving it down. So you can kind of do them in different orders, whatever way will work for you, where you understand it the best. All right, let's look at one more. So we're looking at example 7. Again, we're starting with f of x equals x squared. And we're looking at h of x equals 3 times x minus 2 squared plus 4. So what are we doing right here? Well, that's going to go left or right because it's caught in the parentheses, and it's going to go opposite of what we think, so it's going to go right. 2, the positive tells me it's going up because this can go up and down, so it's going to go up 4, but we're also going to multiply by 3 in there. So I'm going to write the multiply by 3 in between because I want to do that before I go the up part. All right, so here's our x and our y. Let's see. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Let's see where we end up. All right, so our original graph, we're at the 1s. All right, so we need to go right 2. So we're right here. We're going to multiply by 3, so it's going to go up by 3. Oops, wrong direction. Go right 2, and then we're going to multiply by 3. So 1, 2, 3, so we're going to be right there and right there. That just kind of gives me a point of where I'm starting. Now I'm going to go up 4. So we're going to go up 1, 2, 3, 4, and then bring those up 1, 2, 3, and 1, 2, 3. So it should be about right there. And that's the basic transformations that we are doing with our graphs.